Hey guys, welcome to video 42. Today I'm going to derive an algebraic solution for the Q point of the source feedback biased JFET. This is going to be a little bit more mathematically oriented than most of the other videos. I know that's hard to believe, right? But if that's not your thing, that's cool. Just skip to the end and you can see the final results. But for those of you that are interested, the reason I'm showing this derivation is because although the final results are often shown in textbooks, for some reason the authors don't like to go through the derivation. And I don't like to leave any questions for the viewers. You know, I'd rather present more information than less. So with that in mind, the circuit we're analyzing is the classic source feedback biased JFET, as we have shown here. The equations we're going to work with are the transconductance equation, VGS equals negative ID times RS, and you may recognize the quadratic formula from one of your algebra classes somewhere along the line. All right, let's just go ahead and dive right into it. All right, we'll start out with the transconductance equation. I sub D equals IDSS times 1 minus VGS over VGS off the quantity squared. Now I'm going to write this out in long form just to demonstrate where all the algebraic steps are coming from. So that gives us I sub DSS times 1 minus VGS over VGS off times 1 minus VGS over VGS off. All right, now what we're going to do next is apply the FOIL method, that is first, outside, inside, last. You may be familiar with that. And what that gives us is IDSS times 1 minus 2 VGS over VGS off plus VGS squared over VGS off squared. I'm going to multiply through by IDSS now, and that gives me IDSS minus 2 IDSS times VGS over VGS off plus IDSS times VGS squared over VGS off squared. And the next thing I want to do is make the substitution VGS equals negative ID times RS. And for every occurrence of VGS here, I'm going to substitute this in. And that gives us I sub D equals IDSS minus 2 IDSS times negative ID times RS, and I'm just emphasizing the negative sign here associated with the numerator, divided by VGS off, plus IDSS times negative ID times RS squared, which gives us ID squared times RS squared, divided by VGS off squared. All right, now in the middle term here, notice we've got a negative times a negative. These are going to cancel, and that leaves us with IDSS plus 2 IDSS times ID times RS divided by VGS off plus IDSS times ID squared RS squared over VGS off squared. The next thing I want to do is put this in standard polynomial order. That is, I want the squared term first, the first power term second, and the 0th power term last. So, and I'm also going to remove the I sub D factors from the numerators and put them beside the fractions just to make things nice and clear, okay? So what that gives us is I sub D equals IDSS times RS squared over VGS off squared times ID squared plus 2 IDSS times RS divided by VGS off times ID plus IDSS. All right, and now because we're going to be applying the quadratic formula, we want to have 0 on the left-hand side because we're looking for 0 equals ax squared plus bx plus c. So we're going to have to subtract I sub d from both sides, and that gives us 0 equals IDSS times RS squared over VGS off squared times ID squared plus 2IDSS times RS divided by VGS off times I sub d. And now we're going to subtract I sub d plus IDSS. And the reason I did it here was just to associate the I sub d to the first power terms with each other to make it absolutely clear what's going on. I hope, anyway. All right, so what I'm going to do in the next step is factor I sub d out of these two terms. And that gives me IDSS times RS squared over VGS off squared times I sub d squared plus 2IDSS times RS divided by VGS off minus 1 the quantity times I sub d plus I sub d SS. All right, and now we've got our equation in the form we need to apply the quadratic. Okay, so we've got 0 equals this, and remember the quadratic formula is negative b plus or minus the square root of b squared minus 4ac divided by 2a. And with our quadratic up here, a equals IDSS times RS squared over VGS off squared. B is equal to 2IDSS times RS divided by VGS off minus 1, and C equals IDSS. And there we go. When we want to analyze the circuit, we just substitute our circuit values into these equations, put it back into the quadratic formula, and evaluate it. All right, now of course you guys know that I'm not going to leave you with this horrible looking handwriting of mine, so I compiled this information into a nice form suitable for framing, and here you go. All right, so let's apply this information now. On the next page, I've got a circuit using the MPF102 with the average parameters that we derived in the last video. And rather than try and enter all of these values into this horrible Microsoft calculator, I decided to do it ahead of time. And these are the values I came up with for A, B, and C. And putting them into the quadratic formula, we end up with either a drain current of 41.1 milliamps, which is clearly not possible, or 3.14 milliamps, and that's the reasonable solution. Okay, so let's just use the traditional graphical method of determining the Q point and see how close it is to the algebraic method. So let's make our little table with ID and VGS, and starting with 0, 0, our first point is here, and let's use IDSS. That's 6 milliamps, and that gives us a VGS of 0.006 times times 220, which is 1.32. So we'll have a VGS of negative 1.32 volts. All right, and we want to figure out how far to come over here on the VGS axis. So it's 1.32 divided by 0.25 volts per division, so divided by 0.25. We're going to come over 5.3 divisions. Okay, So 1, 2, 3, 4, 5.3 is about here at 6 milliamps. So let's draw our straight line between these points, and here's our Q point. Whoops, let's get the pencil active here. All right, our Q point, and it looks like about maybe what, 0.1, 2, 3, 4, 5, about 0.53 times IDSS. So 0.53 times 6 milliamps is about 3.18. All right, so graphically we get about 3.18 milliamps, and the algebraic method gave us 3.14. The algebra is probably more accurate, but either way, I just call it about 3.2 milliamps or 3.1 and let it go at that. All right, so we do have good agreement between the algebraic technique and the graphical technique. Now, before we move on, I just want to take a look at this in Desmos again for a second, okay? So if we call it up, I'm going to enter my transconductance equation here. Okay, so that's IDSS, which is 0.006 times 1 minus x divided by negative 2.5, and we're going to square that, and here's our transconductance parabola. Now the scaling's not quite nice here yet, but what I want to do next is plot our ID times RS line on here, and actually that's going to be negative ID times RS, but I have to change the form a little bit. It's going to be negative x divided by, whoops, and that is not negative x. Here is negative x divided by 220. And there is our ID times RS line plotted on Desmos. And you can see that the intersection here is given at 3.14 milliamps. And again, what did we have? Well, the algebraic approach told us it was 3.14, and that's what we're getting here as well. So not surprising. But since I've got the entire parabola here, let's take a look and see what that second solution looks like, because that's going to be the intersection of this line with the parabola way up here. And it looks like that's around 45 milliamps or so. And is that the other solution? Yeah, 41.1. That looks reasonable. So I just thought I would leave that on there to show you where this other root gives us a solution. And by the way, that's called an extraneous solution. It's mathematically valid, but physically it doesn't have any meaning, okay? And I hope this was a reasonably enjoyable video for you, and you found something useful in it. And once in a while, the algebraic approach is nice, but it's very cumbersome, and I still prefer to use the graphical approach. And that's what I'll be doing in future videos, unless there's some reason I want to torture myself with the quadratic formula. All right, guys, so I'll see you next time.